Hello, my name is Olga Petrovska, and today I'm going to introduce you to Prawf, an interactive system for program extraction. This is joint work with Ulrich Berger and Hideki Tsuiki, and it is supported by the following projects: Computable Analysis, CoreCon, CIE, and for me personally, I would like to thank EPSRC for my funding. Let me begin with the motivation behind the project. In computer science, we have a notion of Carey-Howard isomorphism, or you can also come across the name Carey-Howard correspondence. This is direct correspondence between mathematical proofs and computer programs. Taking this into account, we thought it would be a good idea to create a formal system that utilizes this correspondence and enables us to extract useful and, what is more important, correct by construction programs from proofs about abstract mathematics. Here I stress on the correctness of the programs because it's a key factor if we want to develop safer software. Before I dive into our own research, I would like to acknowledge work that has already been done in this area. There are already some proof assistants over there that allow program extractions. These include MinLog, which serves as our primary inspiration, NuPerl, Cork, Isabelle, Agda, and so on. Here I would like to point out that MinLog and Prawf have a lot in common. They are both based on first-order logic, while Cork and Agda are based on dependent type theory. You can think of Prawf in some way as a variant of MinLog that focuses on abstract mathematics. Technically, the main but very important difference is in the way how they treat induction and co-induction. In Prawf, we have fixed points of strictly positive operators, and MinLog, similar to Cork and Agda, have clauses. Overall, each of these systems implements program extraction in their own unique way, but the key factor here is that program extraction is regarded in these systems as an added feature, not as a primary goal. And this is exactly the gap that we aim to fill by developing a proof of system primarily focused on program extraction to produce cleaner and more efficient programs. So what is this formal system that we use in our tool? In a sense, it's a modular system. First, we have IFP, intuitionistic fixed point logic, which corresponds to the logic of the proof. It includes definitions of the integral parts like a term, a predicate, a formula, as well as a set of rules that enable users to manipulate these formulas. These rules include the usual intuitionistic, first-order natural deduction rules, as well as induction and co-induction and equality rules, including symmetry, reflexivity, and congruence. Secondly, we have RIFP, which is IFP with realizers. Essentially, those two systems are the same, but RIFP has its additional argument for realizers. A realizer is a notion related to constructivism and intuitionism, and essentially it refers to the fact that if one is to consider a formula to be true, one needs to provide a witness of this, and realizers are exactly those witnesses. We have already presented IFP in our CIE paper in 2018, but I will give a little refresher and comment on our recent developments. As I mentioned, IFP covers the logic part. Since we didn't want to restrict the users with respect to which abstract mathematical objects they want to work with, IFP works as a schema rather than a system with strictly defined sorts and terms. With IFP, a user has the freedom to define their own proof environment. This includes language, context, declarations, a set of relevant axioms, and by language I mean exactly the sorts, terms, predicates, operators, and so on. When defining the environment, the user has an opportunity to add relevant axioms. These axioms need to be non-computational. That means that they should not contain disjunctions. This ensures that a program extracted from a proof that uses these axioms won't depend on their realizers and therefore will be correct in any model of these axioms, of the axioms. Once the environment is defined, the user can save it as a template and use it for other relevant proofs. Once the proof is done, we can extract a program from it utilizing realizability interpretation. If you would like to understand how we define realizability, I would encourage you to refer to our previous paper, Optimized Realizability for Program Instruction, which contains the soundness theorem stating that if you can prove A in IFP under assumptions gamma and delta, then you can prove that some P realizes this A in RIFP under the corresponding assumptions, provided that free variables of P are in vector A. This soundness theorem was subject to some restrictions that are now lifted because of Hideki Tsuike's great idea of introducing the intermediate system IFP prime, which is IFP with slightly improved versions of induction and co-induction. And this system links IFP and RIFP and contributes to separation of logical reasoning from computation. In this new paper, the soundness theorem is redefined and states that if you can prove A in IFP prime, then you can prove it in RIFP under the corresponding assumptions where free variables of P are in vector A. The proof calculus of IFP is free of computation, and there is only one notion of equality obeying the usual rules of equational logic, in contrast to other systems that have various decidable or non-decidable notions of equality. In that case, proof checking is algorithmically very hard and potentially not decidable. In our case, we have the adequacy theorem proven in the IFP paper, and it shows that there is a direct match between the operation and the denotational semantics of programs. So we are constantly talking about programs and program extraction, but what are programs really like? As you can see on this slide, the programs are terms in an untyped lambda calculus enriched by constructors for pattern matching and recursion. In its raw form, the extracted program of a proof is obtained by replacing proof rules by the corresponding program constructors as per Curry-Howard isomorphism that I mentioned earlier. Here it is important to point out that if we just extract the content of a proof as it is, we will have a lot of garbage code that has no computational content. And this is why we distinguish between non-Harrop and Harrop, or it would be more correct to refer to them as Raziova-Harrop formulas. Interestingly, here we can draw some parallels with Koch. If we look at the difference between prop, which would correspond to Harrop, and set, which would correspond to non-Harrop. And with regard to minlog, Prawf has a different realizability interpretation for Harrop formulas. In Prawf, it's Harrop-Ain, and minlog treats these Harrop formulas as if they were non-computational formulas, and that's it. In our paper, we have a very interesting case study on exact real numbers representations and conversion between them. So I really encourage you to go and have a look at it. But now let's go and actually have a look at Prawf and how it works. I would like to point out that we have a website, prawf3.wordpress.com. You're welcome to visit it and check out information on what this proof system is all about. You can also try it out for yourself if you want. There's a manual, there's a tutorial, and of course the source code of our stable version. Now let's get to the actual demo. So what is important to know about Prawf is that we can work in two modes. The first mode is the prover mode, where you actually make the proof and you can extract the program there. And there is the execution mode, where you can execute your extracted programs. We will begin with the prover mode. So I type prover, yes, and then I'm asked to type batch code. What a batch is, it's basically the environment that consists of language, axioms, declarations, and context. And here I already have two batches that I created. The first one is for real and the second one is for lists. So if we look at the real numbers, we have language, we have a sort of real numbers, we have some constants, we have some functions, predicates, operators, and so on. And then we can also define, for example, some axioms. But with axioms, we have to remember that we have this restriction. They should not have computational content. So that's important to keep in mind. So let's say we want to work with real numbers. We select the batch code real. We enter and all of our environment is loading. And before we go to the actual proof, I just wanted to highlight something to you, specifically how we define natural numbers, because this will help you understand maybe better what's going to happen in the proof. So natural numbers are defined as this predicate n here, and it's a predicate on abstract sort of reals. While in other systems you would normally have natural numbers created as a free algebra or a data type. Also in other systems you would have addition and subtraction, multiplication, it all will be defined, but in our case we just have these abstract functions here, you can see. So what is this n really? So we can give a recursive definition of natural numbers as a predicate n, as I said, and here x is a natural number written as nx if and only if x is equal 0 or x minus 1 is a natural number. So you can see this definition here, and here the big X is the recursive variable used to refer to the predicate itself. This predicate is not RIFP because we have disjunction. So this is just some kind of general information that I hope will help you to understand what's going to happen next. So now when it's loaded, I can enter a goal formula. But actually, I do not want to do that because we do not have much time to go through the proof and do it step by step by doing the simple natural deduction steps. What I will do instead, I will use a tactic. And a tactic is a pre-recorded sort of script of a proof. So if I have some tactics here, but if I want to see which ones I have there, I can do this. I can type show tags. Yeah, and here I can see the names of the tactic and what formula it proves. And say I'm interested in this +1, the program, or let's do this addition. So say I'm interested in this addition to run it. We are trying to prove this statement. For all x, n of x implies for all y, n of y implies n x plus y, which represents the addition of natural numbers, and n is actually the least fixed point of phi. This is mu phi, and phi is defined as lambda y, lambda z, z equals 0, or z or y z minus 1. So what I do is I run the tactic. I run the tactic addition. Okay. And here's my proof. So if you want to understand what happened, If you look at addition, we have an existential formula. We do for all introduction, implication introduction, then we apply the induction rule and so on and so forth. And what happened is by selecting the tactic, I just basically reran this whole proof. So we have now this proof, and it's big and kind of long to read. But that's not the main point, because we are here really for extraction. So what we can do, we can extract a program now. So I will type extract. And I need to give it some name. Add, let's say, let's call it add. So now what's happening, we have this transition from IFP to RIFP and then to the actual programs. And if you can see here, you have extracted program simplified, and if you scroll up, it's actually extracted program full. And that is exactly an example of when we have this garbage code, that when we use a distinction between HAROP and non-HAROP formulas, that we can then clean it up to something much smaller and much more readable. Now that we have the program extracted, we can actually see if it works. So let's do this. We need to now switch to the execution mode. So I type exec. So now we are in the execution mode, and we would like to see how our extracted program for addition works. And what we need to do before that, we need to define the numbers that we want to add in the right format. For that, we use the numgen function. So let's say we have some number L, which is 2. And we have some number M, which is 3. Okay, and if we look at it, if we want to understand what they look like for the program, for example, L is 2, and what is important here is basically how many times RT appears. And here it appears 2 times, so left of nil is 0, right of left of nil is 1, and right of left of nil is 2. And the same is for 3. You see, here it appears 3 times. So what we expect is to have it 5 times. Let's apply our program. And I apply this simplified SP program to the arguments L and M. And I can either give it some certain number that I want to see what does this computation equal to at a certain step, or I can just go step by step. But going step by step is a long process. So let's say we put, I don't know, 100 steps. And in 100 steps, we have a complete calculation, and we have exactly as expected, right, 5. So our calculation is right. So just for comparison, if you would like to understand what these intermediate steps are and understand this Curry-Howard correspondence where, using which we have function applied to function to a function, and we have this intermediate result of the calculation. Instead of choosing 100 steps, I will actually try to go step by step. I type S, and first nothing happens, and then, so in the first step, there is no evaluation, there is bottom. It does some evaluations, and I keep on going. and it starts evaluating, but hasn't evaluated just yet. Keeps on going, and as long as you have bot, that means that your evaluation is basically incomplete. It's not the final result just yet. And I keep on going, and here somewhere at the step 44, I already managed to reach my result because I don't have bot anymore. So this was our demo, and now our presentation is coming to an end. But before you go, I would like to highlight some key points to keep in mind. First is that we are using these systems of IFP and RIFP, and they enable us to be more flexible. They enable us to use various mathematical objects. For example, we can do list reversal regardless what elements of this list are. There's this other example of translation between different representations that we present in our paper, and I really encourage you to have a look at it. It's a very interesting example. Second thing that I haven't specifically said, but I would like to highlight here, is that we allow the use of classical logic as long as it's disjunction free. So this is this extra bonus feature that you get on top of the usual intuitionism. And it gives us more freedom, it gives us more flexibility again. And last but not least is, of course, something that I keep on stressing, is that Prawf is built with program extraction in mind. So where do we go from here? First of all, we still need to implement the soundness proof in our system, because our ultimate goal is to extract program with a formal proof of its correctness. Second thing, we would like to implement various extensions, and some work has already been done on them. It's add in sequent calculus, enable concurrent fixed point logic, and so on. And very important thing as well is introducing more theorems, so developing the theorem database in Prawf to make system more robust and easier to use. So these are a couple of points. And if you would like to learn more about what we do, you're welcome to have a look at this paper we are presenting here, our paper from 2018, or paper by Berg and Suwicki on intuitionistic fixed point logic. And of course, I encourage you to visit our website, prawf3.wordpress.com, and there is a lot of useful information there on our tool. And don't hesitate to contact us if you have any questions and you're interested in our research. We'll be happy to hear from you. So thank you for your attention.